Okay, today I'm going to continue our discussion on cache memory mapping, and we learned the direct mapping, and we started to discuss associative mapping. And I want to hear one more time, show how does the direct mapping work in up in cache, and then we move to associative mapping. So let's just have a main memory. Okay, and we have a cache, and the cache memory has four uh, cache memory has 4 blocks. Each block has 4 bytes in it, so it's 4 blocks, and each block has 4 bytes of information. So in total, the cache has 16 bytes, and so start address for 16 address location, we need 4 bits of address line. So the start point is 0000, and the last address is 1111. This one is a cache memory. The main memory has 16 blocks. So 16 blocks. So it's 4, 8, 1, 2, 3, 4, 5, 6, 7, 8, and 16 blocks. And of course, each block has 4 bytes. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so the last one also has 1, 2, 3, 4 bytes. So there's for 16 blocks, time for the 64 bytes. For 64 address line, we need 6 bits to address 64 uh, combinations. So we need 6 address. So it starts from 000000 up to 111111. Okay, so the start point of block 1 in the cache, the start, so block 1, let me change the color. Block 1, block 2, block 3, block 4 of the cache memory. The start address of block, I wish that I wouldn't start from block 1. We should start from block 0, not block 1. Okay. Block 0, block 1, block 2, block 3. Okay. So because block 0 has 4 bytes, the first byte has an address of 0000. The last byte of the block 0 has an address of 0011. Is it correct? Of course, yes, it is, because it's 4 blocks. Block 1 starts from address. Block 1 starts from address 0100 and ends at 0111. It is the like address of block 1. Block 2 starts from 1000 and ends at 1011, I think that you hear me now, don't you? Hello? Yes. Just wait, I find that page. I lost a minute. Okay, finally. So you see my screen and hear me? Just confirm. Okay, good. So the main memory, in fact, has 16 blocks, which is block 0 to block 15. Just I'm writing numbers, block, uh, instead of block 10, I say block A, block number B, block number C, block number D, block number E, and block number F. So F is block 15. So okay, so the addresses for each block in the main memory starts, for example, for block 0, it starts from 0060 up to 000011. The second block is it starts from 0001 up to 000111. Okay, and it continues until the last block, which the address starts from 11110 up to 11111. Okay, so this one is like the addresses for each block. Now we want to map the main memory in the cache. We have two different methods. Sorry, three different methods. We have direct mapping, associative, and associative. Now, for now, I'm going to talk about direct mapping, and then we continue. One thing that is important is that this main memory has a 16 4 bit, 16 4 bytes. Whenever any of these bytes one needs to be just accessed, let's say the byte is here. This byte will be, we need to fetch this byte in block 7. The block that includes that byte will be completely copied to a corresponding block on the cache. Okay, not just that byte. So if we want to access to one address, the entire block will be moved, not just the individual byte. Block number 7, for example, block number 7 is zero. It starts from 0111 00 and ends in address of 011111. Okay, so if we convert these two numbers to if we convert these two numbers to hexadecimal, these two, let's see, if should we convert to hexadecimal? uh, yes, if we convert these two numbers to hexadecimal, block 7 has like a start address of 1, 8 and 4 is 12, 8 and 4 is 12, 12 is C, and the end like address is 1F. So Uh, the block 7 has a start address of 1C and end address of 1F. If any byte in this range get needed by the processor, all the blocks from 1C, 1D, 1E, and 1F will be moved to the corresponding block in the cache. Is it clear? Okay. Now, by the way, I'm talking about direct mapping. Okay. Now, let's say we want to access to some addresses. We want to access to for address 02. We want to what should we do? 02 is 0000 0010. We get this 6 bits because the size of memory is 16. So the address is like here. So if we look to the block, we see that the address 02 is located in block 0, and the entire block 0 will be mapped to block 0 of the cache memory. Okay? So how we should know which block is mapped to which block in the cache? Of course, we have our address fields, which consist of tag, block, and offset. One thing that I should mention is that in addition of the data in the cache, the data also keeps some extra variables information, and those extra is called tag. So tag. Each block has a tag. Okay. So every time we have an address, the address was, let's say the address we have is, for example, the address we have it's address 27, 27 hexadecimal. And we want to access to this address in the main memory and see which block of the cache is corresponding to this block to this address. So 7 is 1110, of course, and 2 is 01. Okay, So we oh, by the way, before reaching to this point, we should see what is the size of each field. What is the size of each field? What is the offset size of the size of offset? Can you tell me what is the size of offset? How we determine the size of offset? We look to the each block and see how many bytes are in each block, and how many bits do we need to address those bytes. Of course, there are 4 bytes in the block, but we need only 2 bits to address those 4 bytes. Okay, because for 4 bytes, 2 bits can combine in 4 different ways. So offset field is 2 bits. What about block field? How many blocks do we have in the cache? We have 4 blocks. How many bits do we need to address one of these 4 blocks in the cache? Again, we need 2. How many is remaining? 2 for offset, 2 for block. The entire main memory is 64 bytes, which needs 6 bits to address. So 2 of them is dedicated to offset, 2 of them are dedicated for block, and for the tag, we have 2 bits for the tag. Okay, now let's when we have this like information, it's time to access to address 27 hexadecimal, and to see which block is like the mapped block of the cache for this block in the main memory. Let's see, 27, because it's 6 bits, we should write 27 in the form of 6 bits. So I wrote it in 6 bits, it's 100111. So let's just put it in the like field. Okay, and here is the answer. The which block number 01. So 27 will move to block number, which block number 1. Okay, block number 1. And what is the tag? The tag is 1010, will be placed in the tag field, and entire block will be updated. Of course of course 0111 with this bar is part of block 1. So we know that this address is mapped to block 1. Okay, so we blocked our information from the main memory to the cache memory. Why 6 bits? Shouldn't be 8 bits, 64. 64. Look at the main memory. Main memory has 16 blocks. Each block has 4 bytes. 16 times 4. 16 times 4 is 64. 64 is 2 to the power of 6. So we need 6 bits. I have a question here. Sorry, I forgot to like mention with the question. Question says why 6 bits for the address on the main memory, not 8 bits? I'm just answering to this question that because the main memory has 16 blocks, each block has 4 bytes. 16 times 4 is 64, and 64 is 2 to the power of 6. Okay, so this one is block. So the next time, if we want to access to another memory, another address, okay, another address, and let's say that address is 37, not 37, 36. The next time we want to access to address 36 in the main memory. Let's see what's gonna happen. 36, of course, is 1 1 0 110. Okay, is it correct? This one is 3 and this one is 4 and 2 6, 36. This one is like the binary address of 36. Let's put it in the address field. If we put it in address field, it's 101 and 11. Something interesting happened here. We see that 27 was mapped to block number 1. And here 36 also is mapped to block 1. Both of them are mapped to the same block. What is the difference between them? They like the tag number is different. So if this time we want to access to address 36, the first thing we do, we see what is the start point, the start address of this block. So 36 is 110110. So start address, start of the block, the start of the block is 110100. End of the block is 110111. So this address is 34 and this address is 37. So you see that if we want to access to address 36, entire block, which is addresses 34 to 37, will be moved to the cache memory. So which block of cache memory? Of course, block 1. And this time, if we do this transition, we have to update the tag because this time the tag number is 1 1. So every time the processor wants to access to the memory, to the information, first checks the cache memory. First checks the cache memory. Okay? And the first thing it does, it checks the tag. Okay? To see if that block, a specific block of the memory of the cache, has the same tag or no. If the same block has the same tag, the information is valid. Otherwise, the information will be requested from the main memory and we will have a miss instead of hit. Okay, so now let me just show you one example. Let's say the CPU wants to access to the address 1 hmm, 1 F wants to access to address 1F. Okay, so what does it do? It puts this information in the fields 1F is here. So the processor checks the block number 3 of cache memory because it's block number 3. Then it is a first step. First step. The second step, check the tag to see if block 3 of the main memory has the same tag of the address. If block 3 of the cache has information and the tag is unique with the um, um, address field, so we will have a hit. So I have a question. Can you explain the conversion again, please? Which conversion? Conversion. I have a question. So it says, can you explain the conversion again, please? The 36. Just you mean how did I convert 36 to the binary? Can you unmute your microphone and ask your question? Okay. So 36. Let's go ahead and explain 36 one more time. The main memory, the processor, let's assume the data in the cache is like has a tag of 10. Okay. Main memory, the processor wants to access to 36. What does it do? 36 is 110110. The processor puts this address in the field and finds the block. Which block is that? Block 1. Checks block 1 to see if block 1 has data or no. Yes, block 1 has data. That's fine. The next step checks to see if the block 1 has the same tag of the address field. Check the tag. The tag of block 1 is 10, while the address tag is 11. So it means that this information is not belongs to address 37 because tag is different. So what's happening? This block has to be just overwritten. So the data, the new data will be overwritten of the old data. So the address 37 from main memory will be accessed and placed instead of the old data in block 1. Okay, so this one is direct mapping, and but it's the binary 36. No, it's not binary 36. I have a question. This one is this one. This one is a binary of 36. Answer is no. This one is not binary. This one is hexadecimal. We should just separate like in group of 4. Okay, group of 4. Do you remember I said whenever we want to convert from base 2 to base 16, we group the bits in group of 4, and each group represents a number. So if we like add 2 zeros to the left, and so this one is represented as like 6, and this one is represented as 2. It's not binary to decimal. It's binary to hexadecimal. Okay, so okay, so now you do a practice and try to access. I keep it here. Try to access to address to address. Try to access to address 3A. 3A. And tell me this address in which block of the cache the parser is looking for this address. Just tell me if the processor wants to access to address 3A, which block the processor looking for. Just 1 minute because it's easy. One answer. I mean, don't send me binary numbers. The block is block 0, block 1, block 2, block 3. Just tell me in which block the processor will look for this address. Which block of the cache? Oh, I got 2 correct answer. I need more. I wait 1 more minute. Okay, I got some answers. That's fine. Okay, let's see. The processor, the the only thing the processor does, just write this number in the binary form. So three is like 1 1, and A is 8 and 2. It's this one. So we just place this information in the field. So it's 1 0 1 0 1 1, and here is the answer. Which block? Block number 2. So the processor will look for the block number 2 of the cache to see if the data is in block number 2. So it checks block number 2. There is no data because the tag is not updated. The tag is empty. So it seems that still nothing is placed in the cache. So we'll get the information from main memory and place it in the block 2 of the cache. Let me erase all this stuff here. I got it. Could we do another example question? Yes, of course. Why not? So let me, it was block number 2. So block number 2, let me just go here. Block number 2, we'll place the information block number 2 and we'll update the tag as 1 1 because tag is 1 1. Okay, and then it search to access to address in the next line. The processor wants to get access to address uh, 1919. So this time, tell me which block of the cache processor is looking for this information. I got one answer so far. Okay, so I got a few answers. So the first address was 3A, and we had a miss because there was nothing there. So the next address we accessing is 19. Let's see what's going on. I got just four answers, five answers. That's fine, but you are 15 students, so I need more answers, but that's okay. So 19, let's write 19 in hexadecimal. So 19 is 01 and 01001. We place this information in the fields, and we see that again it's block number 2. Now let's check. The processor checks block number 2. Fortunately, there is data available in block number 2. In the next step, the processor compares the tag with the tag of block 2. Are they same or different? They are different. So it means that that data is not like the correct data. So we will have another miss, another miss, and the tag, the date, like the block, entire block, including 19, will be moved to the block 2, and block 2 tag will be updated. Block 2 tag will be updated to 0 1. Okay, now let's continue. Let's continue. Two more examples. Sorry. Two more examples. Let's say we want to access to address, let's see which address. Address 2F. We want to add access to address 2F. Let's see which block. Just send me the answer. 2F. Which block of the cache the processor should search for this address? Okay, I'm receiving some just correct answers. Very good. So 2F will be like is equal to 101111. Okay, so the block is 3. So the processor checks block number 3. The block number 3 is empty. So nothing is in block number 3. Of course, block number 1 and 2 have data, but block number 3 is empty. So definitely we will have a miss, okay, because data is not in block number 3. Grabs the data from the main memory and place it in block number 3 and update it like the tag. By the way, when I say we want to get like address 2F, 2F 2F is like 1 byte, but one block will be moved from main memory to the cache. So which bytes will move from main memory to the cache? It's easy. Just keep the tag same, keep the block same, and offsets should start from 00 to 11. So if you look to these numbers are uh, these numbers are uh, 2C, 2D, 2E, and 2F. So addresses 2C, 2D, 2E, 2F, which are in one block of the main memory, all of those will be copied from the main memory to the cache, not just a single byte. Entire block will be copied from the main memory to the cache. Is it clear? Okay. So, so you might ask me, what's the point with the processor? I might have a question like one of you can ask me, okay, processor checks the block, checks the tag, and transfer the entire block. So what's the point of having this offset? This offset is very important because this offset points the byte we need in that block. So this one is the third, where the last byte of the block is the information that the processor needs to access. Okay, the last example that I'm going to give you here is address. Give me a second. Address. Just wait. Okay, the next address is 1B. This time, processor wants to add access to address 1B. Can you tell me which block in the cache memory we should look up for this information? Okay, so let's see. 1B, if we replace 1B in the like in our tag field, B is of course A is 10, B is 11. Okay, B is 11. So 11 is 8 and 3, 8 to 1. 8 to 1. So 821. So this one is like B. Okay, this one is B. So this address is 1011011. So which block we should look for this information? Block number 2. We go to block number 2 and compare the tag. Is the tag same or different? We see that fortunately the block 10, which is block number 2, has the same tag of our address field. Bingo. So we just got the like information available in the cache. We don't need to go to the main memory and grab the data, bring it to the cache because the data is in the cache. It's correct that we haven't access to 1B address 1B before, but how it's possible that 1B is available in the cache? We haven't accessed. So by the way, first let me just write a hit here because we got a hit. So we don't need. So I have a question. Can you tell me, one of you, you can just unmute your microphone or type it to me. We haven't access to 1B before. How is possible that 1B is available in cache? Any idea? We access to 3A, we access to 19, we access to 2F, and then we access to 1B. We haven't access to 1B before, but 1B is in the cache. I got two answers, let's see the answers. So let me just read those answers to you. One of you said, did we already have a value placed for that address? Did we already have a value placed? Okay. Second, because previously entire block will transfer to block 2. Okay, so Tanya says that because previously entire block will transfer to block 2. In which access? In which access it happened? The next one is because we haven't been there. I don't know. The next answer from Brian is like correct, like Tanya answers. It says that the address 19 was in the same block of the memory. That's fine. That's good. That's the correct answer. Not 12, 19. Do you remember we accessed to the 19 before? What is the block of 19? 19 is 0, 1. 19 is 0, 1. 9 is 8. 8001. So entire block for 19 will be this one, and this one. So this one is 19, this one is 1A, this one is 1B, this one is 18. You see, when we accessed to address 19, one block of the information transferred to the cache memory. And if you look, you see that 1B is part of that block. So it's correct that we haven't accessed to 1B before, but because we accessed to 19, we see that 1B is in the same block of the 19. So it's like the advantage of, and it's the reason why anytime we access to a byte, we transfer one block. Okay, and if you remember, we had some rules called locality. It says that anytime we access to a byte, to an address, it's like most likely we will access to neighbors or neighborhoods like in the short time. So when we access to address 19, there is like most likely we will access to address 1A, 1B, 1C, like in a very like short period of time. So it's the reason why 1B is in the address. Is it clear? Okay. Now that we learned, I think we completely 100% learned uh, direct mapping. Let's move to associative mapping. Okay, so associative mapping is like here. Let me just copy this main memory, copy this main memory, and paste it here. Okay, good. Okay. Now I want to talk about associative mapping. How does associative mapping work? So we have the same main memory, but this time the like the cache has a different technique to map the information from the main memory. By the way, the size of the cache is same. The size of the cache is same. So let's just copy the cache as well. Copy the cache and paste it here. Okay. This one is the cache. Some small differences. Let me erase these values and let me erase these tags. Okay. And let me erase these yellow highlights. No. Okay. No. No. Okay, that's fine. Let's keep that line. Okay, so this one is the cache and this one is the main memory. Now we want to see how does associative mapping work. The first thing we should notice in associative mapping, in addition, this one is cache. In addition of the data, we have like the same tag we had for direct mapping, but the size of tag is bigger than the size of the tag of direct mapping. And here we have the address field. The size of address field is 6 bits because of the memory. How many now how to define the fields in this address field in address line. We don't have three fields, we just have tag and offset. That's it. So in direct mapping we had tag, offset and block, but here we have tag and offset. So the offset depends to the size of each block. So in the cache, each block consists of 4 bytes, which needs 2 bits to address. So offset needs 2, and tag is 4. You see, the size of tag is bigger than this, larger than size of the tag in direct mapping. In direct mapping, the size of tag was 2, but here is 4. So how does this mapping work? The difference between direct mapping and in associative mapping is here. In direct mapping, any block of the main memory can be mapped to a specific block in the cache, just in a specific block in the cache. So even if the other blocks are empty, so and we need to use the same block which is mapped for the specific address. But in associative mapping, any block in the main memory can be mapped to any block in the cache. Okay, any block in the main memory can be blocked in any can be mapped to any block in the cache. So whenever we want to start to first access, we place the information in block 0, then block 1, then block 2, then block 3. And then we erase one of those blocks with some techniques and replace the data. So no matter, so if we want to access to address 19, for its example, in direct mapping, 19 always mapped in block 2, okay, in direct mapping. But here, address 19, one time it can be blocked in, it can be mapped in block 0, the next time block 2, the next time block 1, the next time block 3. So like any block can consist like address 19, okay? It's not like direct mapping. How does it work? It's simple. It's even simpler than direct mapping. So we, whenever we want to access to a memory, an address, the processor has to check the tag field of the address with all tags simultaneously. So here is a problem. We need lots of hardware, and it's cost, it's expensive. So if the cache has 16 blocks, we have to compare the tag with the tag of the address with 16 tag simultaneously. So we need some some what's that, some hardware, some gates to do this comparison. If the tag is equal to one of these tags of the cache, the data is in the in that cache, in that block of the cache. Let's do some examples. We want to access to address 110001. We want to access to this address. This address, this block, in fact, moves to block 0 because block 0 is empty, and the tag will be updated as 1100. Then we want Okay, so you hear me? Hear me? Okay, good. So, uh, I said that when we want to access to address in associative mapping, when we want to add to access to address 110001, we place this block in the block 0 of the cache, and the next block will be we will place it to block number 1 of the cache. Okay, and the only thing we do, we place the tag part of the address field in the tag part of the cache. Okay, so the next address, if I want to access to address 111 000, can you tell me in which block should I put it? I got one answer, two, five answers. Looking for five answers. I got two, three, two more answers. Okay, I got four answers. One of the question you asked what was the question? I'm just telling that if the processor wants to access to this like uh, address, so which block this address will be mapped. So I got six, seven answers, and most of you say block 3, which is not correct. And block 2 also is wrong. The correct answer is block 1. I only had one correct answer. Why block 1? Because if you look, you said the tag of the block 1, which we have in block 1, is the same as this new information. So this new information is in the same block which is already in B1. So we don't need to like uh, copy the entire block in B2 because already the information is in block P1. So the this one will be remain in B1 because it is in B1, and so on. And when the cache is filled, no, not B2, when the cache is filled, we need to like erase some blocks and replace the new blocks, which they have some techniques like most recently used, least recently used, LIFO, FIFO, which we can discuss next week. But one thing here I want to, oh, okay, so here we had a miss. We had a miss for the first one. For the second one, we had a miss. For the third one, we have a hit because the information is in the main is in the cache. Okay, just give me a minute. Just I'm looking for something. And here is like a general. Oh, this one is set associative. Okay, I will discuss it next week. That part. Okay, so if the next time, the next one, if we want access to 1 1 0 1 0 0, this time which we compare the tag, which is 1101, with those tags. We couldn't find any match, so we place this information in block number 2, and we will have a miss. Okay, and the next time, if we want to access to 110011, Can you tell me what's going on here? We will have miss or hit. I got a question. Let me read what see what's that. So every time when we move to another entry, we leave data behind, and if we come across the same, we got a hit. What do you mean by leaving data behind? Every time I have a question says so every time every time when we move to another entry we leave data behind, and if we come across the same we got a hit. Every time yeah, every time we come across the same we got a hit. That's correct. Every time the like we didn't get like a same, it's a miss, and we have to access the data from the main memory and bring it and copy it to the cache memory. So this block, is it miss or hit? Can you tell me, any of you? Oh, I got this one. Let's see the tag. Tag is 1100. Let's see. Do we have, oh, before that, I forgot to put 1101, 1101. So now we want to access to 1100. Do we have that tag here or no? Yes, we do have it in the like block 0. And so we say that this one is hit and it's in B0. Okay, and so on. So we can just continue. And in the like in your in the let me open chapter 4. Just give me a second. Download. Just wait a minute. I'm looking for an example. Okay, slide number 40. Slide number 40. I don't know if I have posted uh, chapter 6 on Sakai or no. If I haven't, I will do that tonight. Go to slide 40. There is an example of fully associative cache mapping, and just try to do the example, and it helps to learn it. Okay, so that's enough for today, and we will continue our discussion on the week after.